Good afternoon again, everyone. Welcome to this webinar. So where we will introduce you to the safety requirements when dealing with collaborative robots, also known as cobots. So this webinar continues our topic on machinery safety. In case you miss any of our previous webinars and you would like to watch the videos, so what you can do is you can scan the QR code showing in this slide here, which will link you to our YouTube channel. Then you can watch all the rest of the previous webinars on your free time. So I'm not going to introduce too much about myself. So currently, I'm working as a business development manager for key account customers for Pulse. And also I'm very interested in the automation and the robotics, and also a member of the technical community under the Enterprise Singapore for automation and the robotics. So for this webinar, we are going to talk about a few different topics. First, I will do a quick introduction to the Cobot safety, followed by the Cobot safety standards. Then we will discuss a little bit about the Cobot risk assessment and also the different collaborative methods. And followed by the Cobot risk reduction measures. And the last but not least is safety validation. Then we will also give some time for you to ask questions. And also we will need your help to fill up our feedback form in the end of the webinar today. So let me just do a quick introduction of collaborative robot first. So just now, before we start the webinar, we asked 3 questions. So I believe some of you are quite familiar with this term, collaborative robot. But for those who are not familiar with, just to let you know a little bit more about the definition of a cobot. So a cobot, short for collaborative robot, is designed to interact safely and effectively with humans in a shared workspace. So basically, for a cobot, it will work together with humans in the same working space at the same time. So what's more for a cobot? It has integrated safety functions. So sometimes you will see that the cobot, they have the force sensing, they have the speed and the power limitation. They also have the collision detection, all these safety features embedded. And also the cobot, normally they has no sharp edges. And also they can be programmed easily and quickly for the applications. And typically the cobot is used for tasks such as assembly, inspections, packaging, and material handling. So the question is why we would like to use cobot. So I believe most of you should be quite familiar with the industrial robot, the traditional robot. So why we need to use a cobot in our workspace, in our applications. So I think one of the main reasons to use a cobot is it does help to improve the productivity and efficiency in the workspace. But when you come into cobot, the question is whether a cobot is safe, right? So there's always a common misconception, and that the cobot is completely safe. So ask yourself, the first questions I think we also ask is whether a cobot is safe. So from our perspective, a cobot is not safe by itself. Then definitely there will be a lot of players, especially those cobot manufacturer. They will argue. So why we say a cobot is not safe? So the argument is always like that. The cobot is already designed with a lot of safety features to operate safely in shared workspaces with humans, with operators. But it's important to take note that when it comes into cobot application, the safety relies on proper implementation, maintenance, training, and also adherence to safety protocols. So how to make a cobot application safe? Again, this is also a very important question. It is essential to follow cobot safety standards, conduct risk assessment, implement appropriate safety measures, perform safety validation, provide adequate training, and conduct regular maintenance and inspections. So next, I'm going to talk more about all these relevant parts when it comes into a cobot safety application. So first of all, let's have a look of the cobot safety standards, about the history, about the evolution, and back to the year 2011. In ISO standard 10218-2, it is the first time the standard they describe about the collaborative methods, which is related to the cobot applications. But at that time, the collaborative methods are only described very briefly. But it's good because the main players, the standard organization, they start to pay attention to this new technology, to this new type of robot. When it comes into 2016, there's another standard, or another, we call this a technical specification 15066. This is published. So in this standard, it is described about the 4 different collaborative operations methods in details manner. So this is the first time we describe into details about the 4 different collaborative methods, and also talk about the Cobot safety requirements and the risk assessment of Cobot. And what about now? So now actually there's a new standard, ISO 10218-1 and -2. They are still under development, which supposed to publish last year, but it's not yet published. So in these new standards, it actually talk about the complete robot applications related to a collaborative and non-collaborative tasks, and also describe all this into details. So there's a plan to merge the existing technical specification into these new standards. So I believe all the main players in the market, we look forward to these new standards and hope that will be published soon. So next, we have a look of these 3 standards. I'm not going to talk about the details of all the 3 standards, but if you would like to know more about the ISO standard 10218-1 and -2, it would be good you watch back our previous webinar about the robot safety, the standards and the legislations. But here I would like just to highlight that for ISO standard 10218-1, this standard is aimed at robot manufacturers, and it is also focused on traditional industrial robots. Then for -2, this is aimed at people who install and integrate the robots. So this is mainly the important applied for the robot end user and the system integrators. But these 2 standards both are focused on traditional industrial robots. So when we have this technical specification 15066, what's the main purpose of these standards? This standard actually it specifies safety requirements for collaborative industrial robot systems and also the work environment. And this standard, it is importantly to supplement the requirements and guidance on collaborative industrial robot operations given in the ISO 10218 standard. So when it comes into this Cobot standards or technical specification 15066, and what's the details of these standards? In this standard, actually, it has 7 different crosses. It's very important to take note of 2 sub-cross over here. The first one is 4.3. So this section is talk about hazard identification and the risk assessment associated with Cobot. And under the cross 5.5, it talk about the details about the collaborative operations. So there's 4 different methods are described into details. So we will talk more into details about these 2 the important sections in next few slides. So in this slide, we would like to let you know more about Cobot risk assessment. So when we would like to do a risk assessment for Cobot, we have to consider the following several specific aspects, which is related to the Cobot applications. So the first aspect here is human tasks undertaken inside the application. The second is type of human interaction. It means how human interact with the cobot. And the next is about collision, whether this collision is possible or not. So later we will also talk about for different collaborative methods. Then you know some methods, the collision is not possible, but some method, the collision is possible. So when the collision is possible, we need to take note of two different types of contact. First is transient, another is quasi-static. So later we will also talk about what's these two different type of contact, and also the possible the body position. So it's important to note which part of the human body will have the collision with cobot. And also we need to take note of the transitions between different collaborative tasks, and also the transition between collaborative and non-collaborative tasks. And what's more, we also need to pay attention to payload of the cobot to an vector of the cobot, because they are also very important when we come in to identify the hazard associated with a cobot application. So what's more, I would like to highlight here is the integrator. We talk about cobot integrator is responsible for risk assessment of the cobot application and select the appropriate safety components for the cobot application based on the requirements. And the end user also need to participate in the risk assessment process and the design of the workspace for the cobot and the operators. So next, I will like to elaborate a little bit about the relevant hazards associated with a cobot. So the first one, also the most important one, is collision with a robot, with a cobot. Pushing caused by the robot. So this is very common, including the tools used on the robot. The next is clamping caused by the robot. So this clamping can towards to the table of the cobot, towards to the structure of the building of the environment, and also could happen between the different robot axes. And the second scenario is rescued of a stuck person. So if there's an accident happened, if a person is stuck, so additional hazard could still happen if there's another person would like to rescue. And also unexpected startup of a cobot application, and also the end effector and the workpiece hazards associated with a cobot. For example, if you're using a sharp-edged workpiece with the cobot applications. And then we also need to take note of some of the other hazards, for example, process-specific hazards, for example, high temperature ejected parts or welding the splatters. I'm not going to talk about details how you need to perform the risk assessment for cobot, because for cobot the risk assessment you still need to go back to follow the ISO 12100, which is the risk assessment, the general requirements. So next, I'm going to talk about the 4 different collaborative methods. So these 4 collaborative methods are described in details in the technical specification 15066. So just now, I think in the survey that we did, I think most of you are not familiar with this standard. So I see this is a very good information for you to understand better about different safety feature methods can be implemented for your cobot application in the future. So the first method is called the SMS, Safe Rated Monitor Stop. So in the new version of the ISO standard 10218, this method actually is no longer mentioned as a method, but as a general concept in the entire standards. But in the current technical specification, it still remains as one of the methods. And the second method we talk about, and also for this SMS method, this is normally applied for traditional robotics. The second method is called HGC, hand guiding control. So this is also normally for the traditional robotics, and especially for setup, teaching, and operation tasks. And the next method is called the SSM, speed and separation monitoring. And this is also applied for traditional robotics. And the last but not least is a method PFL, power and force limiting. And this is for the Cobot for collaborative interactions purpose. So just to have a quick summary over here, when we talk about the method, the first two methods, the method, the SMS and the SSM, these two methods, the scenario is the robot and operator, they can perform the task in the same space, but not in the same time. So when the robot performs the task, operator is not allowed to perform the task. When the operator is performing the task, the robot will stop and then not perform any task. So in this case, there's no contact between the robot and operator. That is not possible for collision. And for this method, HGC, this method, robot and operator, they are in the same space and the same time, but the robot does not perform automatic tasks. So this method is mainly used for teaching and the power assistant purpose. But for the last method, PFL, this method, robot and operator, they can perform the task in the same space simultaneously. So under this scenario, physical contact is possible between the robot and the operators. And also for this webinar, we will also talk about all the four different methods, but we will put a little bit more attention for the last method, PFL, this method. So let's look into the first method, SMS, this method. So this method, basically the robot need to stop if person enters the common collaboration space, and the robot will continue once the person has left that space. So from time in which the robot is in the state of a safe rated stop, a direct collaboration between human and the robot is possible. So for example, the person they can enter, but the robot is stopped, but he can do some assembly or maybe to do some changeover of the workpiece on the Cobot. But when you implement this method with your application, you need to comply with the safety distance requirement in according to ISO standard 13884, 857 and 13855. And also, there's a requirement, there's no automatic restart in the detection areas, in the dangerous areas. And also under this method, there's no collision is possible. So just to let you to know better about this application or this method, let's look into this video. So let me play this video. So this is a robot palletizer, and it's doing pick and place to pick the carton and put inside the pallet. So in this method, it's using the laser scanner, and the laser scanner will detect if less operator is under these dangerous areas for these pallet loading areas, and it will stop. It will stop the robot when a person is entered. And of course, what is not showing here is after this person is leave from these areas, then the robot will resume its movement or its operations later. So next, I'm going to talk about the second method. It's called the HGC, hand guiding control. So hand guiding control can only be activated after the robot reaches the hangover position and the stainless steel monitoring is in place. So this is for the safety purpose. So before a person enters enter the collaborative workspace, the robot must have a stop safely. Then the HGC is activated by a 3-position enabled device close to TCP. So TCP is stands for the 2 central point of the Cobot. And the stainless steel monitoring is released by the system. So you need to use an additional enabled device enabled for you to enable this method. And the robot movement is controlled by the person in this case. So when the operator releases the guiding device, a safe rated monitor stop is issued again. And also under this method, no collision is possible. So let's look into another video over here. So the operator is using an enable switch, additional device, and hand guide the robot to the position. So this is where this method HGC is used for the robot applications. So next, I'm going to talk about the speed and separation monitoring. So this is also a very interesting method. So in this method, a robot and a human move simultaneously in collaborative workspace. However, the distance between human and the robot is monitored by safety sensor technology. So normally you need to use additional safety device to measure the distance. So safety based on distance, collision is not possible under this method. And this collision will be avoided by PSD, a presence sensing device, for example, the laser scanner or safety mat or even the safety radar, this kind of area monitoring device. So robot will stop before it come to contact with the human. The speed of a robot varies depending on the distance between human and the robot. So which means you can set a different speed limit based on the distance between the human and the robot. But the robot will eventually need to be slowed down and stops when breaching the safety distance. But it is possible to continue off this motion when power and force limit method is applied together. So which means you can apply additional method for Cobot application. And in the next video, I will show you about this example. So let me play this video. So you can see the robot is doing pick and place. And then the operator is coming and actually it triggers the slowdown of the robot. So now the robot is running at the safe speed. Then this operator can use his hand to touch the robot, and this robot can still run at slow speed. So this is showing you also the kind of a combination, not only about this safe speed, speed and the separation method, but also by apply the PFL, this additional method. In next few slides, I will going to talk about this method, first pressure and the force limiting. So pressure and power and the force limiting. So human has access to collaborative workspace, which means there is possible to have the physical contact with the robot and the human. So as I mentioned, we have two different type of contact, quasi-static and transient. And also this kind of contact can be intentional or unintentional. So contact forces are limited technically to a safe level. So how to define this safe level? In this technical specification 15066, it tells us about this concept. It's called the biomechanical limits. Basically, it defined what's the limits for different part of human body when it comes into pressure and force applied from the cobot. And also, sensitive parts of body should be avoided. For example, scalp, forehead, eyes, or ears, or face. This need to be avoided by using this method. And also, it talk about risk reduction. How to do the risk reduction under this method? We have a passive measures, which is inherent safety design on the robot. And also, we have the active measures, which is about the robot safety functions. So for us to understand better of this matter, we need to understand what's the possibility of collision. Just now we talk about intention and unintention. So intention means you have intended use through the work task, and the intention to have the contact with the cobot. And also less in attention, unintentioned, for example, like foreseeable misuse, or maybe less application error resulting in collision. And when it comes into collision types, we need to understand these two different types. For quasi-static contact is also called clamping. So clamping between a cobot and a fixed structure. So normally you are not able to retract from the clamping point. You are actually trapped inside this when the accident is happening. Another type is transient contact, or we also call this dynamic impact. So contact between operator and the robot where the operator still can't retract. So that is the difference based on the definition of these two contacts. So what's our objective? We would like to make sure there's no injury is allowed when there's a contact happening between the robot and the human. So under passive measures or mechanical measures, what we can do is we can increase the contact surface. We can use inherent safety design of manipulators and infectors. We can also absorb the energy by flexibility of formed materials. And when it comes into active measures, this is more towards internal and external robot safety functions. We can use a safe limited speed. We can use safe torque control. We can also limit the position of the cobot. And also we can install additional collision detection sensor on the cobot. So maybe you will ask how we are going to define these biomechanical limits. So in Annex 8 of this technical specification 15066, it actually lists down about the values, what's the limit value, or so-called the threshold value for pressure and the force, which you can apply under different type of contact. So from these tables, I'm not going to the details, but just would like to highlight that for transient contact, the pressure is normally double. It means the limit is doubled of the quasi-static contact. And in this slide, it's just to show you the graphic figures about the acceptable and unacceptable the force or pressure which you can apply based on the force measurement. So when a collision is happening, at the beginning, we consider it as a transient contact or dynamic contact, normally happening for the first 0.5 seconds. And then you can see it based on this limit of this transient contact. It is doubled of this quasi and quasi static value or limits. So for the after the first 0.5 seconds, it is actually the quasi-static contact. And from this graphic on the left side, the y-axis it is for the force of pressure, and for the horizontal axis is about the time. So you can see it in the red zone. This is the zone for unacceptable value of force and pressure. So for us, when we do the risk reduction for this type of application methods, what we need to make sure is we need to make sure the pressure and the force we measured are fall under this acceptable region. Then next, I'm going to talk about the risk reduction for collaborative applications for Cobot. So we need to look into, first is the design of Cobot. And definitely we would like to use rounded shape, smooth surface, pad surface to absorb energy of contact. And also robots special designed with rounded edge and corners. Robot special joints avoid sharing hazards between axes, and also to have suitable hand-guided control for collaborative applications, as I mentioned just now. And what's more, we also need to look into the layout application design. So this is also important on top of the Cobot itself. We need to reduce the payload in movement if necessary, the mass of an infector and workpiece. Ensure enough space is occupied by the robot system and the operator in the collaborative tasks or workspace. Identify the robot's collaborative space and where the cobot and the human, they will have the interactions. And also avoid unnecessary access to safeguarded space. This is also important to reduce the frequency, reduce the possibility. Provide devices for recovering the lost work pieces. And another scenario is to use external adjustment. So you don't need to access to these areas when the cobot is in the operation. And the next, I'm going to just to talk a little bit more about the end effector design. And this is also the important, actually very important. It means how to design the end effectors, because a lot of hazards, a lot of accident happen is due to the improper design of the end effector of the cobot. So again, we need to focus on rounding the edge and corners, padding and cushioning materials, contact surface as large as possible, distribute force over the foot surface, increase edge radius and modifying edge profiles, use inspection systems like sensor or cameras to avoid intervention of the operator, avoid gripper with clenched fingers or points elements, prevent violent movements by programming, and keep the work pieces held safely. The next slide is talk about the safety function. So risk reduction by safety function is also the very important for the cobot risk reduction. So how to optimize the low ball pass to avoid collision clamping points. And for traditional the industrial robot, this is not that important. It means when you would like to program the robot to move from position 1 to position 2, you can define the path, whatever the path you like for traditional the industrial robot. But when it comes into cobot, we have to consider the possibility of collision and the clamping points. So in the pictures on the right side, you can see there's two different paths, path 1 and path 2. So the path 1, the path 2, it can reach the same final position for the TCP. And but for the path 1 is pounding, is collision, is a transient contact. For path 2 is squeezing, crushing, and it is quasi-static contact. So of course, by considering these two paths, you need to see which path you need to choose, right? Now, of course, it's very obviously in this case, if you have a choice, then of course you need to choose path 1 instead of path 2. What's more, we also need to reduce the dynamics. So sometimes we need to reduce the speed of cobot. We need to use limited force, power, and torque, and comply with the body model. And also we need to have the stainless steel monitoring. And also we need to limit the minimum possible axis angles. So these are considered under the risk reduction by safety function of cobot. And what's more, we also it's also good practice always to restrict the collaboration space. Although the cobot can collaborate, can work together with human in the same place, but we should try to limit where it can move and safeguard to protect sensitive body regions and use a presence sensing device to create transition between the different methods. And the first sensing use of sensitive pads or sensitive bodies to prevent and avoid collisions. So all this can be implemented for the cobot for the risk reduction. Next, I'm going to talk about the safety validation. So after we do the proper risk assessment for cobot, after we do the risk reduction, after we implement the cobot collaborative methods, it's important to understand how to verify that the cobot application is safe on site. So the basic element is again the risk assessment with all the relevant safety functions, what are the hazards, where is the collision with robot, and for validation, it contains a few different elements here. First, we need to check of guards and protective device if appropriate applied, like type, size, distances, reset function, bypass the different modes. And the next, we also need to verify the required performance level. So for Cobot, it's also they have some associated safety function. You need to make sure they can achieve the required performance level. And then we need to do the safety check, like a fault simulation, overrun measurement, and also complete the checklist under the Annex H of ISO the 10218-2. And what's more, for Cobot, you also need to do this collision measurement for collaborative methods application under method PFL. And you need to make sure it is complying with the biomechanical limits of the standard requirements. Then the question is how we can do this measurement, how we can make sure the pressure and the force is within the limits, right? So you need to use a pressure and force measurement device, and in order to help you to verify this part. So in Pulse, we do have this a complete collision measurement set called PRMS. So this also showing on the right side. So this is a complete device or set you can use to do this pressure and force measurement for your Cobot applications. So I'm not going to the details how you can use this, but of course, for testing, you need to test multiple times for the same collision positions. And also you have to make sure the variance is within the tolerance. And in this slide is just to show you the examples when we are using this set to do the measurement of the force or pressure of, if you can see from picture, it's a KUKA, the Cobot. So you need to, first you need to identify the possible collision position according to your risk assessment and where the collision could happen. Then you need to set the force limit to 50 Newton in this example. And also you need to choose the right spring constant based on the collision position with the human bodies. And then for each robot speed, so here on the right side, you can see there's a list of the speed we would like to test. And each speed of the Cobot we test with 10 set of measurements. Then you will get the values. So also we need to make sure all these measurement point is as close as the actual applications. So let's just have just a very quick summary in this case about today's topics about the collaborative robot. So here I will also elaborate a little bit more about our points here. So first of all, collaborative robots are not safe straight out of box. So the Cobot application is the safety is much depends on how you use it and how you integrate with the system, with the environment. And the performed risk assessment is essential, is important for your Cobot application. So I think in the standards, just now I also mentioned about the responsibility and also implement the risk reduction measures. So based on the safety methods, we talk about 4 different safety methods. And then for the risk reduction measure, you can implement by robot, by the layout, by an infector, and also by the safety functions. And last but not least is very important. You need to validate your Cobot application. Excuse me, to validate your Cobot application and ensure the forces and the pressures are not existing the requirements from the standards, from the technical specifications. So maybe another question you may ask is how I can become a Cobot safety expert, right? For Pulse, we provide you with a different level of safety training course, which is related to robot and the Cobot. And here I would like to just to highlight some of our training course for your reference. So we have fundamental of machinery safety. This is under fundamental level. It basically to train you about all the basic safety requirements associated with machinery, but also talk about the robot safety requirements. And what's more, if you would like to have practical experience on risk assessment, right? As we talked just now, it's important to do a Cobot risk assessment. So we also have this workshop as a training course to help our customers to understand better, to have the real application to play with, to understand how to do a proper risk assessment of your machines, of your robot applications. And the next, under advanced level, we have robot safety and integration. So this course provide more advanced knowledge about the robot application. It also talk about the details of the collaborative robot. And also this training course elaborate a lot details about the ISO 10218 standards. And what's more, we also have the workshop for human-robot collaboration collision measurement set. So this workshop is basically to train you how to use our Pulse the collision measurement set to measure the force and pressure of your Cobot applications. And what's more, if you think that's still not sufficient, you would like to become the expert, you would like to get a certification from TUV. We also have this CMSC training course, which we work together with TUV. So this is a 4 days training course, give you a lot of detailed, solid knowledge about machinery safety, 360 degrees, and also talk about the robot safety. And also, if you pass the exam, you will get a certificate from TUV, which can last for 4 years. And this is also a worldwide recognized safety training course by TUV and PUSE. So I hope that information helps for today's webinar.